Hello everyone, I am Anit on behalf of Team Field Boundary Detection. So this is our mid-sem review of our project in which the main track was deploy and review. Yeah. So like the motivation for choosing this project, so we are continuing this project from last three semester, 4, 5 and this sixth. So basically small farms which are basically less in size like 2 hectares and all, which are predominant in Southeast Asia, like contribute to 35% of world's food supply. So they are like, if they are also very vulnerable, and like if any threat comes to them like a disaster, anything, they could like seriously impact the food production, the food security and all those things. Yeah. So it's crucial to map these boundaries. So our problem is basically to delineate these agriculture field boundaries using satellite images from Sentinel-2 data. So you can see this is the image and its corresponding mask over here. Okay, now moving forward. Accurate and reliable detection of field boundaries using satellite image is a critical challenge in modern and precision agriculture. Current methods rely basically on manual and time consuming process, like a person visits, does manual mapping of farms, their size and all. So it would be great if we could automate this process using satellite images. So that's the whole idea. The lack of precise field boundary information hinders the optimized resource allocation and effective land management. So the resource allocation part and the effective land management would become much more easier. You could like track the land change patterns and all those things. Yeah, with this. And automated algorithms like basically deep learning models and all those things would be pretty much crucial in this. Yeah. So why the need is basically simple: the food security, crop monitoring, yield estimation and all those things which we have discussed. Yeah. Okay, so this also targets like these few major sustainable development goals, including zero hunger, climate action, life on land, partnership of the goals, and yeah, industry and all these things. Yeah. Okay, so now coming towards the background research. So the goal was, so we have developed upon few deep learning models which are aligned with the state of the art architecture in field boundary detection. So now the as the track of this ILGC is to deploy and test. So we begin by searching for what open source tools are available in this domain. So this is one of the tool which is not properly visited is by Synergize the Parcelio, in which you can see on the left side the image there are certain satellite tiles. Satellite tiles, these are basically the image mapping. So yeah, so you can see in those limited tiles they have given these field mappings. So yeah, so this is one of the very similar thing which we were looking for, but it's again not open source and not for the whole of the data set of the globe. Okay, so then we also found around and we found this paper. This is called Parks, and which is a deployment oriented AI system for robust parcel level cropland segmentation of satellite images. So this was presented recently in Triple AI conference, which is like a very prestigious conference in artificial intelligence. So what they proposed was, they like first they basically trained a model using active learning approach, and they were increasing their data set and they were using annotation and all those things. After that they did pixel level segmentation, so they used the UNet based model in it. And yeah, this was the segmentation part. So for the segmentation they did like patch generation, so divided the image into certain number of patches. They did patch extraction, then they did inferencing on it, then they did the mosaicing part to do this. And you can see these were the results of the farms, the ground truth you can see over here. Okay, so now the third thing which we looked was, it was like a Chinese contest which is iFly tag, in which they also did similar thing, but they were doing it on a like a much more high resolution of data, in which you can like clearly see how the boundaries are compared to Sentinel where the resolution is of 10 meters. So yeah, so this is basically the input image they are giving. I think it's 0.5 meter resolution, and this is the corresponding mask. So the major novel thing which they were doing was, so in this task of the like mapping boundaries and displaying them over, so the overlap tile fusion. So it's basically a crucial task of like cropping these patches out and mosaicing them. Yeah. So how they were handling is basically using this sliding window sort of an approach. So you can see the three bounding box are coming in this patch. So they are only considering the one in which the top left corner is coming inside the box. So in this one it's not coming, in this one it's coming. So this was one of the approach which we figured out from the literature, which we can use and go forward. Yeah. And yes, it, yeah, they used a mask RCNN based model in the back end, and they have used other backbone as well with Coco and all those things. Okay, now moving towards the work which we have done till last sem. So as I said, we started with fourth sem, and yeah, so these are some basic conventional CV approaches which we use initially, along with like getting familiar with data pre-processing and stuff. So this is a basically Sobel kernel and like traditional computer vision techniques, and we were like getting zero point 0.6 or something sort of the accuracy in this. Yeah. Then in my summer internship, I continued this project under Professor Shashank's mentorship, and then we like did some experiment regarding the benchmarking using UNet, mask RCN, and all ResUnit based models. So this was a work which we did, and yeah, then we moved to the first vision foundational model, which is SAM, which was released by Meta AI in the April of last year. So it's basically an instance segmentation model which you can see over here. So yeah, so we started with it. So giving a brief architecture, it's based on VIT. It's a visual transformer in which there is an encoder, decoder, and prompt encoder, and also a mask decoder in which you can give different sort of prompts. And yeah, this is all. So our experiment was aligned more towards input adaptation, in which we adapted our input and all those things. So yeah, it was done using mixers, and we optimized it using dual anything. So you can see a linear and non-linear mixer. Okay, so these were the SOTA results of it, which was like UNet and ResUnit were performing better in our AI for boundaries dataset. Okay, then we begin prompting. So this is the image, the results without prompt and all. Then we tried different prompts in which we gave the, what you say, the single image prompt, the output of ResUnit as a prompt, and like grade points as prompt, and we got different results. But bounding box emerged out to be a winner in this case. But giving bounding box is again a hassle, so we need to do certain bounding box elimination using IOU thresholding and area based thresholding. So after like using bounding box as a prompt, we were getting much better results. So then we like, so this was for the whole decoder fine tuning and all along with the prompts. But in this part we were keeping the encoder freezed. So now we explored the literature and figured it out, like we could use adapters which will provide the local information to make our results better. And in this they were using fast SAM in SAM adapter. So we did few experiments, but the result was not quite good because it's on lesser parameter. We also did some work on temporal mixing and all, and these were our results. So you can see. Okay, so what is the major work done during this semester is, okay, it's a 3-track work. So the adapter works is being taken forward by Sambar Shikhar. He's a PRF at Plaksha with Center of Precision and Sustainable Agriculture. And I am writing the research paper, which is like the progress so far which we have done. And my other two teammates along with me are working on a tool which we talked earlier for deploying this state of the art model which we have developed so far. Yeah, so these are the basic milestone which we have done, like literature review in the week one. Then we explored the Streamlit and Map integration part. Then I was writing the paper and they were doing the data ingestion part and so on. Then we went into land use and land cover classification, all those things. And yeah, and then we further added some functionalities in R2 which you'll see further. Then we did the inferencing part, chunking our data, mosaicing it, then integrating the whole pipeline.
Hi everyone, I'm Vishal. I'll be explaining the pipeline of the tool FPD tool, visualization tool that we have been trying to make for visualizing the inferences of our model. So I'll be starting off with explaining all of these things one by one. But as an overview, I'll be discussing data ingestion, LULC integration, that is land use land cover integration with our tool, masking the raster data, and then splitting the raster data into smaller chunks, then doing inference on those raster chunks, applying connected components for getting bounding boxes, then doing elimination on those many bounding boxes, then finally combining all those bounding boxes to give out a overlay of masks and put it on Streamlit. So first we did data ingestion. We wrote this pipeline using GEE, that is Google Earth Engine, and Planet API. And so here you can see if we specify a very large shapefile, we'll get out for a specific date time range, we'll get out the satellite image from the Planet API and Google Earth Engine. So after once we get the raster file for a specified date time range, we also found this data set that was publicly available for the land use land cover from 1992 to 2020. So we basically use that to specify our region of interest only on those areas where there is like agricultural use of the land. As you can see, so these different colors represent different areas. So one may represent urban area, the other may represent vegetation, and the other may represent agricultural use, where vegetation being any sort of scrubs or trees. Moving forward, the first major part of the pipeline is masking any raster file that we have and extracting the specific region of interest from that big raster file. So imagine you can having a huge raster file, or in other words, the huge satellite data corpus for, let's say, the district of SAS Nagar. And if you want to restrict yourself to the Mohali region, which is in itself is quite a big of a region, you would, so in this you can see the SAS region and a bit of Chandigarh combined into a raster file. You extract a specific shapefile, you extract our tool extracts a specific area of that raster file, which we are calling the region of interest, which in itself is a huge area. Now since our model is not able to take things other than 256 by 256 pixels, we split that region of interest into smaller chunks of 256 by 256 pixels by doing this chunking. So our tool, so as you can see here, the same image gets sort of chunked into 4 different sections, where these black areas is like padding, and on the right, extreme right, you can see this same image but with a higher resolution being chunked. So we have 2 different versions of this image. This one is a higher resolution image, so we're getting more number of chunks for the same 256 by 256 sector, you can see. So once we have each of these sectors, we then apply our model that we have trained on these different sectors and get out 2 things. One is the different masks, or you can say layers, and we also then get the combined mask or the boundaries from this. So this is like the inferencing part. Once we get these boundaries, what we do is we draw using connected components, we draw bounding boxes onto these fields. As you can see on the right here, the number of bounding boxes that we're getting from this connected components method is huge. So we do a filtering in the backend where we eliminate bounding boxes with the upper limit on the area and also a lower limit on the area of the bounding box. So finally we get a smaller number of bounding boxes. We then use those bounding boxes to get out a mask uh, or
In
a
this video,
shapefile.
I'll be demonstrating the use of tool FBD. So let's start. This is the code for our tool. It's in Python language and we'll be displaying the whole tool on Streamlit platform. Here it goes. So this is the basic UI of our tool. This is the logo, tool FBD, and in this place we can drop our shapefile that we want to plot. So this is the map on which this shapefile is being plotted, and this is an interactive map, so one can move the map, zoom in, zoom out, and that's it. So over here in the base map section, there are 4 base maps from which one can select from, and the first one is OpenStreetMap, then CartoDB Positron, this one, then CartoDB Dark Matter, and Google Satellite. So for different purposes, one can open different base maps. It's basic. We'll be changing it uh, with more functionalities later on. So yeah. So this is the Google Satellite base map, and let's show the mask. So this is the mask that we have obtained from the backend, and the yellow area represents the fields, and it's displayed like this on the map. So let's try changing the base maps. So it looks like this, this, and this. So yeah, that's how our tool works. Thank you.
So in future, we aim to deploy our tool FBD on scale using GE and Vertex AI. Also integrate the tool FBD as a package with XC, the native remote sensing stack of Center of Precision and Sustainable Agriculture. Also host the tool using AWS EC2 instance and making it open source. Also collaborating with Sambal Shikhar on writing the research paper with our findings and getting it published. So the challenges that we are facing are data handling and processing, integrating integration with external APIs and services, performance optimization, resources management, user interface and experience, scalability and deployment. Thank you.